Hello and welcome to our lesson on vectors in the Cartesian plane, or vectors in the plane. We're going to talk about some terminology first, but like some of the previous lesson, we're kind of scratching the surface here. I want you to have a basic foundation and understanding of what vectors are, why we need them, and then as you progress through some higher levels of mathematics, you'll see them applied to numerous situations. So some terminology to get us started. When we have a quantity that is just defined by its size, or we can say its magnitude, we call it a scalar. So like length or area or mass, for example, when you calculate a length or an area or mass, it's just one number. And it's one number to define what that is. So we call that a scalar. But there are some quantities where that's just not good enough. Some quantities, they possess magnitude and they possess direction, like force or velocity. And when your quantity possesses both magnitude and direction, then we want to represent that with a vector so that we can show that magnitude and that direction. Now, in a two-dimensional plane, again, this can be carried out to other dimensions. We're scratching the surface here, okay? In a two-dimensional plane, so on the Cartesian coordinate plane, vectors are often represented by directed line segments with arrows so that you know where we're starting and which direction we're going. And each directed segment has an initial point, again, so we know where it starts, and a terminal point so that we know where it stops. And at the terminal point, instead of seeing an actual point, you will see an arrow. So the arrow is the terminal part there, and the end point, or an end point, is actually the initial point. Okay. Now, since a vector is characterized entirely by its direction and magnitude, a directed segment could have specific endpoints, but it's not really restricted to that specific location. So what I'm trying to say is two vectors with the same length and magnitude, length is magnitude, magnitude and direction, they have the same magnitude, so the same length, and they're going in the same direction, they're considered equal no matter where their initial and terminal points are on the coordinate plane. Okay, so for example, I'm looking at u and v here. These are going to be two equal vectors. So this is a vector. We have, let me try to, we have initial sides. I'm going to try to identify some of this for you. Initial points, not sides. And then we have some terminal points. So we can see where these vectors start and where these vectors end. So our initial points are actually they look like endpoints of a ray. These are actually called directed segments. And then the terminal points are, the arrow is showing us where we land. So that would be the terminal point there. That would be the terminal point there. Now these are considered equal vectors, even though they have distinct locations for their initial and terminal points, because they have the same magnitude, that is the same length, and they're going in the same direction, they're considered equal. And in fact, I can draw any number of these particular vectors. So for instance, if I wanted to draw another one here, let's say I put another one here, and if I did that, I have the same initial point, the same end point, same magnitude, not same initial and end point, sorry, same magnitude, same direction, even though my endpoints have moved locations, because I have the same length and direction, these are all considered equal. So let me say, I called this one u. So the length of each of these, if I use the Pythagorean theorem on any one of them, right, let's say I use Pythagorean theorem to find the length here. This has a length of 1, this has a length of 1. So if I wanted to calculate the length of u squared would equal 1 squared plus 1 squared, which means u is going to be the square root of 1 plus 1, or 1 squared plus 1 squared, which ends up being the square root of 2. Now that's going to be the same for v, and that's going to be the same for w. And so we would say that u and v and w are all equal vectors. Okay, these would all be the same. So the length of a vector, what we just calculated there, that radical 2, that is its magnitude. I guess I should have used the word length up here, not to confuse you too much. But length is the same thing as the magnitude. Okay. And sometimes it's also referred to as the norm. I don't really like that word, but this is notation. So for that norm or that length or that magnitude, it's like a double absolute value, it kind of looks like. So that double bar is notation for the magnitude. So we can say that, let me back this up, make this a little more official, that the magnitude for u is equal to the magnitude for v, that's equal to the magnitude for w, and all of those had a magnitude of radical 2. So these would all be considered equal because all of them have the same magnitude. Okay? Now we're going to look at some basic operations with vectors. Fortunately, they are very intuitive. Okay, very intuitive. Oh no, don't die on me, pencil. So for example, I have two vectors here. I have u and I have v, and I know the direction and I know the length just by the picture. And so the first one says to depict negative 2 times u. Negative 2 times u. So negative means go in the opposite direction, and then 2 means go twice as far as you did originally. So just like what you would think. So if u goes 2 units to the right, then negative 2u would go 4 units to the left. So I'm just going to pick a place on the graph here and draw a vector that starts and goes 4 units to the left. So that would be negative 2u. Okay, it's twice the length of u and in the opposite direction. The negative means the opposite. Okay, so there's that one. And now the next one, it's mostly intuitive. So 3 times u would be 3 times the length of u. If I wanted to add that to v, then I would take the end point of u, or it's the end point, which is the initial point of u, and add it to the terminal point of v. So 3 times u, so instead of being 2 units to the right, would be 6 units to the right. And I'm just going to tack it on here to v. So 2, 4, I lost count. 2, 4, 6, there we go. And oh, I thought I had my cheat tool on. There we go. So tack that on there. Okay, so if I combine u, that green one I just drew in there as that, or tack it onto vi. The green one there I drew is 3 times u. That's the same direction, just 3 times the length. If I add that onto v and put the initial point on the end point of v, and the actual sum of those connects the two to make a triangle. So this length right here is actually representing that sum. So this is what we would call 3, whoops, cheat tool, 3u plus v. So a segment that conjoins the two there is how we represent, I can't talk, the sum for those two. Kind of intuitive. Maybe not as intuitive as multiplying and changing direction, but if we connect the two that we're trying to add, and then connect what's left there, that is the sum. And then subtraction would work similarly. So if I have u and I want to subtract v, let's think about this as a negative v. So a negative v would have the same length as v, but go in the opposite direction. So think about this. Instead of having to go down 4 and then left 2, the opposite would be up 4 and then right 2. So I want that connected to u. So I'm going to take u here, and again, instead of down and to the left, I'm going to go up and then to the right. So my pictures are going to run into one another. I'm going to go up, 1, 2, 3, 4. Let me put my cheat tool back on. 1, 2, 3, 4, and then to the right. 1, 2, 3, 4 to the right 2. Here we go. 1, 2, 3, 4. This is where I want to land, okay? Sorry, I'm making a mess. Now I need my cheat tool. So there is a negative v. So if I have u and I connect that to a negative v, then the next segment that I can put in there to connect those two endpoints that are still remaining, that is what we would call u minus v. I really got to get better at this. U minus v. And now my pictures all kind of run into each other there, but hopefully you kind of see what's going on. I guess I could have planned that out a bit better. Okay, so 3u was green, and then v, the whole sum I did here, was in gray. And then u, I did... It's already there. V, I did in pink. And then in black, you see U minus V. Okay, so kind of intuitive in my opinion. But here are the general rules, right? If you take U and V, or you take V, then U, you could see on the picture that you would be drawing the same triangle, basically. So addition, that holds for normal numbers, like the property, the commutative property says we can change the order we add, still get the same answer. That's going to be true for vectors. The associative property too, we can move things around and still end up with the same answer. Adding 0, not going to affect anything. And then a u and a negative u, those would be opposites, would cancel each other out and leave you with 0. And then if we're going to multiply by scalars, again, pretty intuitive. You can just distribute your scalar. Okay, same thing here. You can distribute your scalars. And commutative property, doesn't matter the order that you multiply, you're still going to end up with the same result. Multiplication by 1 is an identity. Multiplication by 0 is 0. And the last part here is if you have the magnitude of u multiplied by a scalar, it's the magnitude of u multiplied by the absolute value of the scalar. Again, I think it's all pretty intuitive. Now, what we're just looking at there is useful to have a basic understanding of vectors, but it's really more useful the further you go to put a vector in what we call its component form. The component form of a vector helps us to do more analytical work, less graphical work. It's more like, how do we use these vectors in equations, and how do we do or perform these operations without having to sketch out graphs. And so when you're determining this component form of a vector, it's basically to determine the components of a vector you have to look from your initial side to your terminal side. But basically you're looking for displacements. So displacements of vertical and horizontal lengths. And that might be a weird word for you, but I say it so nonchalantly because I've seen it a bunch. So what you're looking at is sort of like when you're counting slope or rise over run. So for example, when you're looking at v, if we start here and go here, the same picture we saw a second ago, to get from that initial point to that terminal point, I would have to go down 4 and I would have to go left 2, or I could go left 2 and down 4. But in either way you go, the vertical displacement, so vertical would be we're going down 4, so we would represent that with a negative 4. And the horizontal displacement would be we're going to the left 2, and to the left 2, that would be represented with a negative 2. And so if we're going to go down 4 and left 2, if the horizontal displacement along the x-axis is a negative 2, and the vertical displacement that's along the y-axis is down 4, then our component form for v, so I was looking at v first, would be negative 2 and negative 4. So not the coordinates, this is what we call the component form, and we're going to put it in not parentheses, but we're going to put it in these little partial triangle looking things, okay? So that's, they sort of look like V's for vector, tells you from your initial point to your terminal point, how are you moving? So you would be interpreting this as left 2, and you would be interpreting this as down 4. So this is along the x-axis, this is along the y-axis. Okay, now if you didn't have a graph to look at that, then you can also find that vertical displacement and horizontal displacement by counting, or subtracting, I mean, just like you would with your slope formula. So this point, for instance, is at 0, 4, and then this coordinate here is at -2, 0. So if you took 0 and subtracted 4, 0 minus 4 is -4. If you took -2 and subtracted 0, -2 minus 0 would get you -2. And so you'd be looking at -2, -4. It's very similar to your slope formula. Okay, you're kind of counting the displacement, the rise, and the run. It's a very similar concept. So we would do the same thing if I wanted the component form for u. So I'm not going at all up or down, I'm only going to the right 2. And so if I'm just going to the right 2, then I would have a positive 2 for my horizontal displacement, my displacement along the x-axis, and not going up or down means a 0 for my vertical. Okay? -2 times u now in component form. The rules are, again, very intuitive, just like we talked about before. I put them all in the box here, but I want you to see what's happening here. -2 times u in component form is just like -2 times u when it's in the coordinate form. You're just going to double what you're given. So if you took the 2 and 0 here and multiplied by -2, then 2 times -2 would get you a -4 here, and -2 times 0 would still be 0. And then here again in component form, 3 times u, so 3 times u plus v. 3 times 2 plus, we would add the corresponding component for v, but this is probably too much to do without 2 steps. So let's do 3 times u first. If I tripled u, 2 times 3 is going to be 6. That was so... I don't know why I'm having trouble drawing these right now. That's going to be 6, and then 3 times 0 is still going to be 0, so there's 3 times u. If I want to add v, which is -2, -4, I'm just going to add the corresponding components. So the 6 and the -2 would get me 4, and the 0 and the -4 would get me -4. So again, very intuitive, kind of makes sense what we should be doing there. And then u minus v. So u is 2, 0, and we're going to subtract v, which is -2, -4. And so we'd be looking at 2 minus a -2, that's 2 plus 2, which is 4. And then 0 minus a -4, that's 0 plus 4, which is 4. Okay? And then the last part here is the only one that might not be completely intuitive. If I want the magnitude in component form, it comes from the Pythagorean theorem. So in the same way we found the magnitude earlier, we had u squared equal to 1 squared and 1 squared. It's the same concept, except now we're looking at not just x values or y values, we're looking at component values. So if u was 2, 0, then this would be the square root of u1, this is u1, this would be u2. So it's going to be 2 squared and 0 squared. And it's 2, 0, right? Yeah, okay. So somehow I thought I had the wrong point there. And so 2 squared would be 4, and the square root of 4 would take us back to 2. And then for v was, I forgot, -2, -4. And so this is, v1, and this would be v2. And so our magnitude would be the square root of -2 squared and -4 squared. So that would be the square root of 4 and 16, or the square root of 20, which would be an acceptable answer, but we probably should simplify. This is 4 times 5, which means we could make this 2 radical 5. And obviously that could be approximated with the decimal as well. So either way. Okay, but all very intuitive. Again, this is just kind of scratching the surface. Once this moves into 3D and you start applying it to trig and equations, it can get a little complicated. But the key for you right now is to understand that a vector is magnitude. It's giving you direction. It's from your initial point to your starting or to your terminal point. How are you moving? Basically, what direction? Okay, and the positives and negatives in our 2D plane tell us those directions. All right, so hopefully you got enough to get you going and get you, again, a little bit of a foundation with these vectors. If not, reach out. I'm here for you guys. Till next time, take care.